So it's my pleasure to introduce Jia Shi. Jia Shi is a vice president of Exadata development at Oracle. Exadata is an engineered system that provides the best performance, scalability, and high availability for running all types of Oracle database workloads. Jia led the team that developed Exadata's X8M's industry-leading performance using persistent memory technology and Rocky networking to deliver 19 microsecond SQL read latency. So we're all looking forward to your talk, and I'm going to let you take it away.
All right. Thank you so much, Joel. I hope you can hear me fine, right? Yes. Okay. Awesome. Thank you, Joel. So this is Jia. I'm super excited to be here today to be given this opportunity to talk to you all about persistent memory, I guess. And as you can see from the title slides I have here, it's under the hood of an Exadata transaction. So I wanted to take you on an adventure today. Let's go take a close look at an Exadata OLTP transaction. I wanted to share some secrets in how we have harnessed the power of persistent memory and be able to transform our OLTP application performance. There we go. So before we get started, I wanted to introduce you what is an Exadata. So some of you may not be familiar what an Exadata is, and then here's a visual picture of it. So an Exadata is a fully engineered system where we believe it's the best platform to run our Oracle database workloads. So as you can see on the left-hand side, this is a rack, a full rack of Exadata. And those are the industry standard racks that you'll see in a data center. And then inside of the rack, we pack a bunch of database servers, which is where the RDMS software runs. And we also have a bunch of storage servers in the same rack. And for the database servers, we have sort of two flavors. One is a 2-socket that with Intel Xeon cores, and the other is an 8-socket, which is like a small SNMP server that really enables us to be able to do better consolidated database workloads and whatnot. And on the bottom is a storage server. So we have two types of storage servers. One is we call high capacity. What that is that it's basically a hard disk-based storage, but we also throwing plenty of NVMe flash so that we can build a flash cache to help provide better I/O performances for our database workloads. The other kind is extreme flash, which basically the storage is all flash. So compared to disk, it's a lot smaller, but all of your data are on flash, so it's super fast. All right, connecting these two are the super cool 100 gigabits RDMA over converged Ethernet. So this is Rocky. I think a lot of people may be familiar with this name, and I'm going to talk a little bit about this technology a little bit later in this presentation. And then last but not least, right, we're in this PIRL, persistent memory talk, so we got to have persistent memory. So each one of our storage servers, we have a 1.5 terabytes of persistent memory in there. And then we make a heck of use out of them in our platform. So I'm going to tell you a bit more exactly how we combine the powers of persistent memory and Rocky to really make a huge difference in terms of the OLTP application. So this is our high-level strategy that we would like to make sure that we can deliver this extreme value add to our customers in terms of we provide the best ideal database hardware that scales out. It's optimized with optimized compute and networking and storage. Then the second piece of software is really dear and near to my heart because I'm a software developer and I love building algorithms that greatly and vastly improve our OLTP analytics and consolidation performances. And we also offer automated management to make sure that a customer has a great end-to-end user experience. So a quick slide about scalability. So I showed a rack in the earlier slide, but this is not the full story. So we actually have this linear scaling capabilities of our storage servers as well as our database servers. So if you needed more storage, what we do is you can just add in more storage servers and then grow your rack into multi-racks as needed. And the way we actually balance the data is we take all the data, we chop them up into smaller allocation units, we stripe and mirror the data across every single storage media in our storage servers. So that gives us this linear scaling of both capacity and performance. A similar story is there for our database server too. So if you need more database processing powers, you can add more storage, add more database servers, and elastically grow your cluster, the database cluster that way as well. Okay, so here is a quick slide about, Exadata actually has been shipping for more than 10 years. And what I'm here to talk about is the latest and greatest PMEM with persistent memory that we have just added in late 2019. And these are all the great customers that we've had on Exadata, we currently have on Exadata. And as you can see, we have been trusted by our customers to run their most mission critical workloads. So enough about Exadata. Let's talk about OLTP. So let's go under the hood, as I had mentioned earlier. So for those of you who are not database geeks, let me spell it out for you. What is an OLTP? That's online transactional processing. Okay, what does that mean, Jia? What is an OLTP application? So I like you to meet a, for lack of better name, I call it a supercritical OLTP application. So what does such an application do? I just throwing some, very silly examples here. Let's say Ben wants to deposit $1,000 to his bank account. Alice wants to withdraw 500. Bob wants to transfer some money. So this is a typical OLTP application where a user wants to perform a transaction through this app in which the database does the actual transaction processing. So hopefully that's a very simple, easy to understand picture here. Now let's drill down and take a look at one such user. Let's meet Ben, okay? Ben is our main character here today for this story where he wants to deposit $1,000 to his bank account. He's super excited about that. So what happens when this request goes into the database server? So as you can see on this slide, the database server gets an update SQL from the supercritical OLTP application. And what the database usually does when it gets a SQL is it has to figure out, what is in the statement? What do I do? So we call it parsing. We parse the SQL. And that operation is usually pretty fast because all the metadata that we need to parse the SQL is usually readily warmed up in the memory of the buffer of the database server. So we build a cursor in memory. So a cursor is simply basically a plan of how we would execute the SQL. Next step, I'm going to go ahead and figure out, okay, where is Ben's account? So generally, we usually, a well-known index type that we build in databases like a B-tree index, right? And then you can have a primary key lookup, which is basically a key in the tree where we're able to kind of traverse the tree and locate a data record. So in this case, let's say I use Ben's user ID perhaps, or account ID to try to locate his record. And usually, because those index trees are accessed very frequently by various different SQLs, so all those blocks holding those indexes, in particular the speed tree, are usually readily cached in the buffer cache of the database server, so in the DRAM cache. So again, the processing is super fast, right? It's at memory speed or perhaps even at CPU cache speed. Then finally, I walked down my B-tree index. I discovered, I found Ben's account. And I'm ready to do the update, right? I want to increment his balance by $1,000. But what problem do I have now? Look, this is a common problem for a supercritical OLTP application, is that the data I wanted to manipulate, either I want to read or update, may not be readily available in my main memory, because my buffer cache is limited, right? It's bound by the memory size. So not every single data block, like not petabytes or terabytes of data can possibly all fit into my buffer cache. So it's pretty frequent and often that I may have a miss in my buffer cache. So when I have a miss, what do I do in those cases? Where is my data? I know this is not an interactive session, so I'm going to be talking at you a lot. So I'm going to ask questions and answer them myself. But all right, so I asked myself a question: where's the data? And as a lot of you would know, yes, the data is in the storage. So what happens if I want to fetch the data from storage, where I have this user account block for Ben? Well, I call it, we fall off an IO cliff. The reason why I call it an IO cliff is that for the prior 3 steps, as you can see, they're all very fast, right? Because I never have to leave the CPU or the memory, right? Like I'm performing at like memory, CPU cache, CPU speed. So it's super, super, super duper fast. But as soon as I get a miss in my data in the buffer cache, I have to go to the storage and perform an IO. And I'll show you in a sec why I call this an IO cliff. So let's take a look. Challenge number 1. What is the IO cliff for this kind of a random data reads? So a database so maybe a quick word about what random means in here. Random means it's not a sequential scan. I'm not going to the storage and say, oh, I'm going to scan terabytes of data. They're all sequential IOs. This random data read is saying, look, I really just want a single AK block that contains Ben's account record, and I just want that block alone. So traditionally, this random data read has been extremely challenging for hard disks, right? Because even though the data is stored there persistently, to fetch that data from a hard disk, you got to go, position your disk head and then endure, the seek latency, the rotational latency before you can transfer the data. So it's already like 3 or 4, maybe 10 milliseconds later before you can actually get the block, AK block out of a hard disk. So that's definitely not a viable option for a supercritical OLTP application, right? And then since then we've had gone like a better technology called Flash. So let me show you how this works in the traditional way of when we have a flash cache. So the database server will issue the data read to the storage server, and the storage server will probe. And let's say Ben gets lucky, his data is in the flash cache. So what happens is that I didn't draw on this slide, just avoid cluttering, but there's a massive amount of data stored in the hard disk. So what we do is we take the hottest data, the most frequently accessed data from the hard disk and cache them in our flash. And that's why we call it a flash cache. And more often than not, we would find our data that we need to read are in the flash cache. So we can go ahead and just perform a local read from the flash and then be able to get that AK block and send it back to the database. And once it's back in the buffer cache of the database server, then our processing can come back to the CPU speed, right? The stall is no longer there. We'll go ahead and be able to increment the balance as needed. So now I'm going to ask you, how long do you think this supercritical OLTP application had waited for this random block read? Not in the case of hard disk, just from the flash. How long did it take? All right, let me help you to break it down. So when you actually do an AK block read from a database server to a storage server, these are the software stacks that you have to go through. So there's always, you send a message from the database application to the storage server to say which block you want to read. And then there's a user to kernel context switch. The message travels over on the wire, reaches on the other side. The storage server software picks it up, figures out where to read it from on the flash cache, goes ahead and issue a read, and then send the block back. So there's a ton of IO processing on the software stack to kind of deliver this AK read. So if we just look at the raw latency, if you're just reading from flash, through a local, IO submit and IO get events to read the completion, it typically takes less than 100 microseconds on the latest generation of NVMe flash. So that's pretty fast, right? But what is this end-to-end latency from the database point of view? How long did the app have to wait? So I normally have people guess, but I have to, review the answer. It's actually 200 microseconds end-to-end usually. And if you can do the math, you'll see that, yes, there's 100 microseconds that's spent not in the raw flash read, but in all the network round trip, the user to kernel context switches, the network IO interrupt processing and software stack overhead. So there's quite a bit of overhead. But since the raw latency is around 100 microseconds, well, 200 microseconds not too bad, right? And if you actually look around, this is a, by the way, this is a data sheet number we put out for our flash-based, prior to our PMAN generation, we say we can get to that latency. But if you look around the industry and look at all the other scale-out storage vendors that's out there, I believe 200 microsecond is already lightning fast, super fast number. So how do I conquer this IO read cliff? Because 200 microseconds to, a thread who's stalled waiting for it is like, a very long time, right? So I'm going to bring you two mysterious guests to our journey today. The first one I'm going to introduce is, I think all of you are familiar with, this is a persistent memory DIMM. So what is a persistent memory? Everybody has talked about this. It's a new silicon technology. It kind of positions itself very nicely between DRAM and flash. In some way, it has the best of the both worlds, right? It reads much faster at almost at DRAM speed, not quite, but almost. But the good thing about persistent memory is that write stores to the persistent memory can survive power failures, unlike DRAM. So they're more like flash in that regard, and they can be used as persistent media. With that said, I just wanted to highlight one thing is that a novel user may not be, or an experienced, let's say, user may not realize that not all stores are equal when it comes to persistent memory. As was discussed earlier, in the current generation of the hardware platforms that we have, CPU, like stores that's still in the CPU cache that haven't, been flushed to the persistent memory DIMM are actually not persisted across a power fail. So what that means is it actually requires special handling and then special instructions to make sure that those data are flushed or bypassed from the CPU cache when we do the stores to persistent memory. So those are super critical. And second is that there's also perhaps a well-kept secret in terms of the right atomicity unit size for a persistent memory. I'm going to touch on that later, but it's not the same as a traditional storage like flash or disk, and they require special algorithms to make sure that you can actually write your data in an atomic fashion. So with those notions explained, I want to point out, so one of the things that we really took pride in is that we carefully studied all of this and integrated, added all those sophisticated algorithms in our own software to make sure that, hey, our writes to PMEM are indeed persistent, as it's super critical for a database to not to lose its data. So now I'm going to introduce a second player in this dynamic duo. This is called our RDMA. So RDMA, in its full name, means Remote Memory Direct Access. So I've drawn a very simple sort of a sketch here that try to illustrate what an RDMA is. And to put it simply, to do an RDMA, you need two things. One is you need a RDMA-enabled NIC. So these are the NICs that is capable of performing RDMA. And then once you have those NICs installed on your server, you're able to register, take a memory region. It can either be from your DRAM or can be from your persistent memory. You can register that memory region on this RDMA-enabled NIC. We call it RNIC, on this NIC. And then once that's done, between those two endpoints, shall we say, that we first have to establish a RC connection. And once that connection is set up, then let's say in this case, the database is a client and the storage server is a server. The database server is interested in performing direct access to the memory of the storage server, either through a read or a write. And then you can actually just do that. And when the database server performs RDMA read or RDMA write, what's neat about that operation is it's completely driven from the client side. And the server doesn't actually get involved at all. So you can think about the memory regions somehow tethered to the card, to the server's NIC, so that when the client comes in and then does the read or write, it can just feel free to do that. And then the storage server doesn't have to spin up any process, do any kind of processing, no interrupts, nothing. and all that can just happen super quickly. So it is a very powerful technology, and we use it extensively as part of our acceleration for OLTP, which I'll talk about in a short minute. All right, a quick word about Rocky. This is just sort of a basic information slide, shall we say, for those of you who may not be intimately familiar with what is RDMA over converged Ethernet, so short, Rocky. So those of you who have actually dabbled in the space of RDMA are probably familiar with this technology called InfiniBand. And then RDMA was, first only, when Exadata started more than 10 years ago, we're looking for a networking technology that gives us three things. One is super low CPU overhead, because back in the days, I don't know if you guys remember, but if you try to pump a lot of data through Ethernet, even if you have multiple links, it would just hog up your CPU because there's nothing that's offloaded to the hardware. So everything was done, through the host software and CPU, and that's just not a good choice. So we wanted very low CPU overhead, which InfiniBand delivered with RDMA. Second, we want to really make sure that it has high throughput. So back in the days, InfiniBand was, always had a lead over Ethernet in terms of the network bandwidth. But now the gap is completely closed. Ethernet just as fast as InfiniBand. And third thing is we really want to make sure that we can perform RDMA because it gives us really low latency and very high throughput. So that's why, the choice we made to pick out our networking was InfiniBand, and then we've been using RDMA for a long time. But now, when we looked at last year, 2019, when we looked at our networking technology, we felt like it is really a good time to cut over to use Rocky, to use RDMA over converged Ethernet, because all of our application that we have built can work transparently on top of this network switch, because as you can see in this diagram, it's really the lower half that gets swapped out. And as far as the API that the user application uses, it remains mostly the same. And it really gives us an edge in the sense that in nowadays, if you go to any like on-prem data center or cloud data center, I would bet you that the default choice for their networking solution is probably Ethernet, right? Not InfiniBand. InfiniBand is kind of an island on its own. So when we switch over our network fabric to Ethernet, we are able to have a cake and eat it too, in the sense that we can retain the great throughput, low latency, low CPU overhead, all the amazing benefits of RDMA, while still be able to allow our network to be integrated into the whole data center Ethernet network, which is quite appealing. So that's why we made the choice and cut over to Rocky. All right, so now, hopefully you haven't forgotten Ben or the IO cliff yet. As we previously talked about, when the data is a miss in my buffer cache, I go to storage to read the data, and then I follow by IO cliff. So how does persistent memory and then RDMA help me out here? Let's take a look. This is a echo of the prior slide where we say, look, end-to-end latency is 100 microsecond in all the network and kernel IO stack, and 100 microsecond latency in the raw flash. So one of the quick way of solving this problem is probably pretty obvious, right? What if we just drop in persistent memory cache, and we'll put PMEM in our storage server, and then we build a persistent memory cache on top of flash cache, right? So I have 25 terabytes of flash, I have 1.5 terabytes of PMEM. So I'll build a tiered cache. I take the hottest data and stick into PMEM. So when my AK comes and I want to read bands block, I say, look, my local latency to read from a persistent memory is much lower. So here I get two numbers. 1.6 microsecond is what you get if you read a local PMEM DIMM, on your same CPU socket. But sometimes your data may not be in the same CPU socket and may be sitting on a DIMM that's on a remote socket, on the second socket. In those cases, you have to go through the QPI, and then we get about 2.4 microseconds latency in those cases. So on average, it's about 2 microseconds. So that's really fast, right? And then if you compute, if you take the numbers and you compute to that, hey, what is my IO cliff now? right? I actually cut it by half, right? From 200 microseconds, I'm down to 100 microseconds. But what is kind of, I guess, less than satisfactory here is that you look at the PMEM latency, it's 2 microseconds, but my end-to-end latency is still 100 microseconds, you know? Like all of my, you know, the savings I had from PMEM cache is not fully reflected in my end-to-end latency. So it begs the question, I do better. So what about we try something more radical? And I introduced back the RDMA notion that we had before. So remember RDMA that allows you to do remote direct access to a piece of remote memory. So what can we do here? In this case, what we have done is we enable the database application to directly do an RDMA read for to the PMEM on the storage server over 100 gigabits Rocky. And when that happens, the end-to-end latency gets further reduced in a more dramatic fashion. It's a 10x faster latency. I call this less than 19 microsecond latency here, but that's actually measured when we have millions of IOPS going on, you know, on our rack. But we have seen, you know, if your load is, you know, you're now doing millions of reads, then you actually would see a much, you know, an even better improved number, like in the neighborhood of, you know, I don't know, I've seen 13, I've seen 15, I've seen 16. So it's just simply amazing. It's you know, great. And let's take a look on how we can actually accomplish that. So remember Ben's transaction, we got a miss in the buffer cache. So the first step we do is we need to figure out if we can actually fetch it directly from the PMEM cache. So that's actually the tricky part of building this feature, because if you're sitting on the database side, you really have no clue where your data sits on the storage server side, right? So how do you perform the RDMA? Where on the persistent memory are we going to read to get the data I want? So before I start with that, I actually, it's a two-step read. I first do a probe of an RDMA-able hash table that's on my storage server. And that will tell me if I have a miss or a hit of this particular block I'm looking for. So if it is a hit, in case, you know, Ben gets lucky, I can just directly issue a RDMA, AK RDMA read of that PMEM location and then fetch the data back. In this case, I initiate RDMA, the data gets back, and then no storage software side, any of the processing is involved, and then I complete my read. Well, that's the happy path. In the case where, let's say this is the first time I'm reading this block from the storage through RDMA and the data is not in the PMEM cache. So when I probe, I will get a miss. And then when that happens, I will actually just fall back to the traditional way of sending a message to the storage server. And in that case, the storage server is smart enough to go look for that data, perhaps in the flash cache, and send it back to me. So I still get the block back in 200 microseconds. But the neat thing that also happens on the storage server at that point is that I'm able to populate that buffer into my persistent memory cache. So the next time the database has to go read that same block again, guess what? It'll be readily available in the PMEM cache, giving you the sub 19 microsecond latency via RDMA. All right, take a look back at our picture. So we have this, you know, fast in-memory CPU processing of my transaction. I falls off an IO cliff. What happens? Now I have RDMA, I have PMEM. It kind of gives me, I call this maybe a trampoline. It gets me over to get my data into in memory with sub 19 microsecond latency. And then I'm able to actually continue processing once the data is in the buffer cache. I'm really happy. One quick word about how we actually ride on the trampoline, I guess, or jump on the trampoline, shall we say. So what we have discovered is that it really depends on your application. But for our database process, it's actually really cheaper to actually just spin on the CPU to synchronously pull for the RDMA completion. I think the mileage will vary based on different applications. But for us, we have a lot of CPU cache, you know, sort of presence. So if we have context switches and whatnot, it turned out to be a lot more expensive. We yield and wait for the interrupt to come in and then wake up again, gets rescheduled, bring back all my context. It actually burns more CPU and gives us a longer IO latency. So for us, it's actually surprisingly easy for us to do here is we just spin on the CPU and wait for the RDMA completion. And there we go. It's cheaper and it's faster. So we're really happy with this one. So this is a slide that kind of summarizes the feature I just talked about. So this is pyramid that, you may be able, it's a little bit not super contrasted, but there's a pyramid here that kind of showcases we have data on the hard disk. We then have a flash cache that really caches all the warm, I guess, hot data. And then the hottest, the cream of the crop, the hottest data gets cached into the persistent memory. So we can actually provide our database with the best performance. And we're also really careful about what to put into the persistent memory because it's also limited in size. You may remember I mentioned that our data is mirrored everywhere. So when there are multiple mirror copies, we make sure only the primary copy is in the persistent memory. So we maximize the working set that can fit into the PMEM cache. And then we also have our management server that takes care of all the, it talks IPM-CTL, it talks NDCTL, it creates the regions, namespaces, DAX devices, whatnot, so handles all of that. And we also have end-to-end security when it comes to RDMA, where we make sure that, hey, and not everybody on the database server can do RDMA. You can only read the data in your own protection domain that allows you to perform the RDMA. So it's secure end-to-end. All right, so let's take a look back at the span story. So are we at the end of it? Not really. When you look at a database transaction, there's one very important property. We call it the asset property. And then you may ask, what does that mean? So in this case, we really care about D. D stands for durability. So what is durability means that, hey, not only do I increment the balance for Ben here from 2000 to 3000, I also have to make sure that it's persisted, it's durable on persistent media. So the way to do that is we have to commit the transaction. So the supercritical OLTP application will send a commit to the database. And the database, guess what, has to perform a write again. I'm so sorry, but I have to reveal to you another problem that we have here is that we fall off the IO cliff again. Because the storage server is where the redo log resides, where all the persistent redo gets written to. So there's no way that I can commit a transaction without performing another IO. So here comes my OLTP challenge number 2. I always wonder if lightning can really strike the same place twice. But as you can see in this story, yes, it does. Unfortunately, not only does it strike the random data read as we talked about, it also affects redo log writes. So let's take a closer look at how redo log writes is performed today. When you send a redo log write to storage, you say, okay, this is what's in the transaction, and then perhaps you piggyback a commit with it. And then on the storage server side, we actually have, prior to persistent memory, we have 2 types of persistent media inside the storage server. The first is flash, as you have learned, and the second is the hard disk. And for our hard disk, we actually have a disk controller that has a persistent DRAM cache sitting in front of it. So that provides a great way to accelerate the log writes. But the problem is that, you'll be like, okay, I can send my writes to flash, I can send my writes to the controller cache. Which one do I go? So what we have seen is that these are all storage devices and they can get into a glitchy state temporarily, meaning they could produce outliers where writes are temporarily stalled. And we don't like that because outliers have profound implication on our database application side, and we don't want that. So to avoid the outliers, we actually send the log write to both devices. And whichever device finishes the write persistently, we can send the ACK back to the database. So this effectively says that for 99.999% of the case, I will never have an outlier because the double outlier, both flash and the controller cache are glitchy simultaneously is the only case where I get an outlier. So that's unlikely to happen because these are independent, low probability events. And when you multiply them together, essentially you get a very negligible chance of hitting that. So in those cases, I'm happy I get the redo committed and that the supercritical OLTP application can notify the user of a transaction commit, and then we're done here. So here I'm going to ask you the question about the IO cliff. Why do I call it IO cliff? How long did the supercritical OLTP application had to wait for the log write? Well, as you can see, the paradigm is very similar to what we went through before, right? When we dissected a random read. So the latency, as you would have expected, is very similar. It's around 200 microseconds as well. So now let's take a look at the IO cliff again for the log writes. Again, as you can see, even though we had managed to trampoline over using RDMA and then PMEM to get sub 19 microsecond latency for my transaction processing, I get stalled again. You know, I would run into a grinding halt again because I would fall off the IO cliff of log writes. So can the same dynamic dual, PMEM and RDMA, help me here? So the answer is yes. What we do is we also employ a similar strategy, and they use RDMA to write the redo logs to the persistent memory on the storage server. So in this case, again, this is a NIC-to-NIC communication. And as you can see, what we have on the storage server is we have a bunch of PMEM log server. They're from persistent memory, and they're like the receive buffers posted to a shared receive queue on the storage side. And then once the redo lands in one of those buffers, the NIC simply sends an ACK back saying, yes, your writes are persisted, you're good to go. So this is super neat, and then gives us a much lower latency because at that point we can notify the user that, hey, your transaction has been committed. And in the background, leisurely, the storage server will be able to destage the redo that was previously that had previously landed in the persistent memory log buffer to its backing store, being the flash or the disk. And once the redo has been drained or has been destaged, that buffer became empty, right? And we can post it back to the same share receive queue to receive future redos. So this is a trick that we have implemented to allow us to really use very small amount of persistent memory real estate and in a reusable fashion to support a very high throughput rate of log writes. So now log writes, you know, as durability D in the asset property demands, it has to be durable. So we have to look at some failure scenarios. So what happens if there's a power outage? Let's say that the database server has gone the ACK saying the redo is committed, but then the storage server crashed. Is my redo safe? So let's take a look. As I mentioned earlier, ensuring that your writes to PMEM is persistent is actually not a totally trivial thing. You can't assume that. So by default, on our servers, we use Intel servers, there is this quite neat technology called data direct IO. What that does is allows a network card to be able to land its receive through either a write allocate or update into the L3 cache of the CPU. And then that really boosts a lot of application performances because they'll find their data, you know, readily available in the L3 cache and be able to process it right away. However, the biggest caveat here is that this data is not persistent in the CPU cache. So we can't not afford to do that if we use PMEM log. So how do we ensure that our PMEM log writes are persistent across power fail? Yes, the obvious choice is that we have to turn off or disable data direct IO. Unfortunately, on the platform that we have, there is a single global knob for every PCIe device. So this gets turned off globally. So even if the NIC card may be lending writes to DRAM, that also, you know, it doesn't get a chance to make it into L3, goes to the DRAM main memory as well. So we actually do see performance impacts to other networking protocol that was, you know, not PMEM related, but as collateral damage because we turned off this global knob, and we have to come up with creative engineering solutions to mitigate those impacts. So I just want to mention it for you guys to be aware, but this is definitely a very important decision that we made because, you know, to ensure the durability, we have to make sure that the data is persistent. Now, I want to talk about a little bit on the networking side. So there are different type of database workloads that may require, IOs or traffic to the storage. Talked about the low latency ones for the log writes. And then there are medium priority, which are the OLTP data reads, which is the first IO cliff we talked about. And then there's also the third kind, the high throughput. I didn't even mention here because those are lower priority batch backups, type of workloads. So if I have a lot of those traffic going onto the same network, how do I ensure that the most critical messages gets to the storage first? Like, my RDMA log writes gets there first. So the way we do is we use different class of services for different type of messages. And because we have a fully integrated stack, we carve out buffers, like network receive buffers at every single switch, every stop along the way, and at the end receive NIC to make sure that those different type of messages go on different traffic classes. And therefore, even if you might be running high throughput workload with backups and whatnot, that could possibly jam up that lane that it runs down, the redo log write travels on a different VIP lane. So it's never getting blocked by that. And always we guarantee low latency that way. So the smart network prioritization is super critical to ensure that we have very low latency for the log writes. So now let's take a look at the Benz transaction, right? Here is IO cliff. Instead of falling off the IO cliff, I do my trick again, RDMA write to the PMEM log. And that is 8x faster than what we had before. And this I'm extremely happy with. And if you look at this whole picture, now that you've kind of done this journey with me, you see, look, the RDMA read gives me sub 19 microsecond latency. RDMA write gives me 8x fast log writes. I turn an IO bound workload into an almost CPU bound workload, right? And that's super, that's a big transformation. So the question goes, are we done? I will say yes and no. So from Ben's point of view, he is done, right? He got his money deposited, the transaction's committed, it's durable, can't ask for anything more. But from the database point, it's actually not done because there is this dirty block in the buffer cache, right? The block that has been updated. Eventually, it has to be, either aged out to the storage server or done through a checkpoint. So here comes our challenge number 3. You may wonder, hey, why is it so hard about writing data back to persistent memory cache in the storage server? How hard is that? So let me introduce a notion to you. I don't know if everyone here knows this word splinch, but if you, follow Harry Potter's Wizarding World, splinching is this, this unfortunate event. If a witch or a wizard were to disapparate and apparate unsuccessfully, part of their clothing or their body may not be may have been left at the former location. So in other words, if we were to apply it to the database world, it's like I have this block, right? The Benz account balance block, AK block, that is sitting in the DRAM of my database server. I need to write it down to the PMEM of the storage server. And it's critically important that we don't fracture that block. We don't have a splinch. You can't leave an eyebrow, in the old location and just have the partial update. But as I mentioned earlier, PMEM is very tricky here because it has only an 8-byte atomic write guarantee. So, and database blocks are much larger. And how do we prevent a splinch here? So let's take a look. First, you may ask, can I still do RDMA? I would say, no, don't do that because it's clearly a bad idea, right? RDMA doesn't involve any storage server-side software processing. If you look at the network, it may have an MTU that's less than your 8K data size. So your 8K writes will be fragmented into multiple fragments when it gets sent over the network. So how do you guarantee that your storage server doesn't die in the middle of it and having, part of your block return, part of unwritten, and ending up with the splinch? So if you go to Hogwarts and they'll get you into this advanced lesson of apparate and disapparation, and the teacher will teach you that you need to follow the 3D principles. It's called destination, determination, and deliberation. So let's take a look, see if we can apply the same 3D principle to help us prevent a splinch when we write a block to PMEM. First, the destination. the database figures out that, hey, I need to send this AK data block. So I don't do RDMA, I make a smarter choice. I send it via a regular message to the storage server. The storage server, upon receiving this data, figures out that, look, this data resides in my PMEM cache. So in order for my database to be able to do RDMA reads later, right, in case I need to bring the block back into buffer cache again, I better update the block in the PMEM cache. So how do I do that? Deliberation. I design a series of strategies to make sure that I don't have splinching. So what do? The trick is that we call a staging rate. So what happens is that we first carve out some staging buffer on persistent memory, and we write the 8K block to that staging area. So once that write is completed and made it safe to the ADR domain, we go ahead and write the 8K in the actual PMEM cache line. So there are two writes. And what happens is that, okay, let's say there's a power outage here. So if the power outage happens when I'm still doing the first write to the staging area, you'll notice that the block in my PMEM cache is still intact. So it's good. I haven't had any damage. My data is still there. When my server comes back, I'll toss away whatever partial blocks in my staging area, and then database can reissue the write. Not a big deal, right? And what happens, the nastier case is what happens if the power outage happens when I'm writing to AK into my PMEM cache, and that left me with a fractured block in my PMEM cache line. I can't let a database read a torn block, right? That results in data corruptions. So what do I do in the recovery case is when the database when the storage server comes back, I go ahead and perform a write from my staging buffer, because remember that one was already completed. So I have the complete AK in there and reapply it to the PMEM cache line. So that ensures that even if I had a partial write prior to the power outage, I'm gonna have a good, complete, atomically written AK in my PMEM cache line for subsequent database consumption. So that brings me to the next slide about how do we ensure persistence across a power fail if the writes are issued from a CPU core. Previously, we talked about data direct IO, which is through a PCIe IO transaction, and here we use the NT store, which is the preferred way for us because we actually don't examine the data. These are just we're storing those AK data in the PMEM cache for the database to read, so it doesn't make sense to bring it into our CPU cache. And based on our performance numbers, we have seen that when you store a large amount of data through sequential writes, NT store far outperforms, if you just do a regular store through the CPU cache and do the CLW plus SFANS. So that's why we stick with NT store here. While we were sticking with NT store, one thing we discovered, which is quite interesting or unfortunate, we spent actually a lot of time struggling on this during the early development days. There are cases when the database may get into a write storm, meaning a workload is changing, the caching content is being adapted to a different type of application. So a lot of writes happen. And what we discovered is that hit the yellow chart, the yellow line here, is that we have pretty good performance of write performance to a PMEM DIM when the number of threads count is pretty low. But as soon as the thread count exceeds some threshold number, and then we hit this precipitous fall, like a 10x performance degradation in terms of PMEM write throughput. And we notice that because our PMEM writes are actually slower than our flash writes at that point. We're like, what gives? What happened? So we worked with our Intel team, and then we were told that there's this knob in our BIOS called IO directory cache. So what that does is it enables this IODC, IO directory cache, to cache the directory updates for PMEM cache lines. So this is especially useful when you issue writes from a remote core. So without IODC, every write is essentially two writes because you have to perform a write for the directory cache state update in addition to the actual data update. But with IODC, it's able to cache the directory update in the CPU cache and be able to piggyback that directory update along with the data update. So it's a lot more effective. And then that moved us to the red line there. So as you can see, the performance drop is greatly mitigated but there is still a discernible difference. So this is kind of interesting because we're used to disks and flash, and then we know that the classic way to saturate a device there is to load it up, right? Schedule as much work as possible, and then once you saturate the device, it stays saturated. But with PMEM, the lesson is different. Don't saturate it too much, because if you have too many threads, your performance is actually, your write performance is actually worse. So now that brings me back to the conclusion of my presentation here. This is the full kind of journey we've had with the 2 IO cliffs that we managed to kind of stay away from. And a lot of you, some of you may have a question about, hey, Jia, why are you so sensitive about the IO cliffs? Think about Ben. He's on his mobile device. He's probably taking a lot of time, just to perform a transaction. It'll take milliseconds, if not centiseconds, for his mobile to find the next nearest cell tower. So what about those IO cliffs? What are you talking about? So I wanted to clarify that this Ben's transaction is really a sort of simplified, silly example to illustrate the story here. But in the real world, on Exadata, we have seen a lot of supercritical OLTP applications, for example, real-time fraud tracking or real-time analytics when user clicks on screens and things like that. These are supercritical applications that really, gets hurt by those IO cliffs and require extremely low latency, extremely high throughput to meet their application demands. And for those applications, having PMEM RDMA are really a big game changer. So this is the last slide I have to summarize what we discussed today. We have OLTP on Exadata. We go under the hood and looked at exactly how an OLTP transaction gets executed and accelerated on the Exadata platform with persistent memory and RDMA. And I wanted to say that how to have a cake and eat it too is we have 99% of persistent memory is used for PMEM cache. So that allows us to create, as big of a working as possible. And because we reuse the PMEM log buffer, so we really only use less than 1% of the real estate for that. And then with 100 gigabits Rocky, we get 10x better transaction processing with sub 19 microsecond latency, 8x faster log writes. And with just a full rack, we can get to 16 million read IOPS, and it scales pretty nearly linearly as you add more and more racks to it. So that brings me to the conclusion of my talk today. I really enjoyed being given this opportunity, and I hope you found this journey fun and interesting. And Joe, I guess I'll turn the mic over back to you.
Yeah, thank you so much. Unfortunately, we're virtual, so we can't clap, but thank you. I know that the chat has been very active during your talk. I think it's indicative of how interesting this talk really was, especially for this audience. So thank you. I see Yitzhak had a lot of questions over the course of the talk, so I'll let him, I guess, prioritize, so to speak. And go ahead, Yitzhak.
Yeah. Okay. First of all, thanks for a truly interesting talk. I have general questions. One is, there is a trend, for example, by Mellanox, now NVIDIA, to increase the functionality of both NICs and switches so they can do operations inside the network, and they claim database stuff, among others. Your architecture seems to keep the communication hardware strictly to communication. Is this a trend that you're planning to consider, or you think it should stay that way?
Yeah, so it's a really good question. And we definitely see that a lot, right? And then they basically have those cards where they call it smart NICs, right? Not only they do the networking, but they also have ARM cores on it, right? And then be able to offload like database processing, and there could be a bump in the wire. What we see is that that's definitely an opportunity for us. And that requires kind of a different, how do I say, like when I can probably go back to that slide, but when a traditional database application is getting processed, you can see that it needs to draw data from very different places, right? Different pieces, buffer cache and main memory, execute a cursor. So it's not entirely clear or straightforward to kind of offload that inside the card because of the limitation that the ARM core can process. It's like, it's so much faster to do it on a CPU core. But with that said, we do see there's actually opportunities for leveraging that kind of technology, especially for things like network encryption, right? So if you think about it, if you want your data, let me take an example of network encryption. For RDMAs, you don't necessarily want your data to kind of flow in the clear on the network, right? And then you want to be able to maybe, you know, enable IPsec over on your networking to say, look, I have a secure tunnel, I have end-to-end security. With that, I see, there's a lot of promises in the sort of the smart NIC ability to offload those kind of processing. And you don't have to chew up a CPU core. Because if today, I bet you go on hardware, whatever hardware you have, if it doesn't have like, this kind of IPsec offload onto the NIC, you can see your query, like we did an in-house test. It took like 6x longer or 8x longer, something like that, some tremendous slowdown. So I think these are the specific areas that's kind of sweet spot for the NIC vendors where they can add a lot of value by offloading this kind of processing to the NIC itself. But as far as it comes to, doing a hash join, walking down a B tree index, I feel like this is still the sweet spot of, getting it done on a CPU core.
Yeah, I think the architecturally interesting question is not so much the NICs. There the trade-offs are obvious, but in the switches, because there the data meets. Data coming from different places actually meet going through the same switch, and doing things in the switch, that's an architectural change. More complex, but maybe things that can really reduce latency or even traffic beyond the trade-off of do it in an accelerator or CPU, as is the case in a NIC. So that's another thing they're talking about. I don't know too many details, but I think that's a possibly bigger change.
I'll have to research more on that. The exposure that we've had is more about, offloading into the smart NIC. Switch is kind of tricky because, Switch, honestly, like we have Exadata that runs on-prem and on cloud. Switch is always a sensitive area because you really want to make sure that, your switch administrator can't sniff your data, right? It's like, it's kind of a common piece of infrastructure. Like, don't do too much there because it's once the switch is exposed, it's not just you, it's everybody else who uses the switch. So, so that's why, if you ask me to predict, I'm not sure if we're going to embed Exadata in a switch in the near future. It's more likely leveraging all those capabilities offload into the hardware on the NIC side.
Okay, another question, then I'll defer to others. And if there's time at the end, great. If not, not. There's another Israeli company called Vast Data that's doing storage, and they're combining persistent memory with cheap flash, so that they end up being cheaper than all flash with higher performance, because they do many interesting things in the PMEM, not caching, all kinds of processing, deduplication, etc. So my question is not necessarily in the strict OLTP context, maybe more general database context. Do you see, again, your architecture seemed to be, okay, we move from hard drive and flash to maybe flash and PMEM, with PMEM being as a cache. Okay, but they're doing something different.
Part of it, and then we have a log accelerator.
Whether it makes sense, whether and the puzzle pieces can fit, or these are totally different approaches.
I'm not, so, okay, we've also had customers asking us, oh, Jia, why don't you just get those, one day per, like one write per day kind of cheap flash drives and give us an all flash solution, right? So that's it's kind of a tricky thing to do. So what we actually really feel like, when you think about your data, like if you have terabytes or petabytes of data, not all of them are going to be accessed, right? We really believe in this tiered caching strategy because that's really where you get to have your capacity, but still run at memory speed for most of your workloads. So, and to be able to, like, for the longest time, we feel like, the way that we have built is a linearly boundless scaling story for the storage. And be able to do that, we mirror and stripe all the data everywhere. So anytime you add a new storage server, you go ahead and just kind of spread out your data evenly that way too. But that scaling inherently calls for a network, right, between the storage and then the database. So the network is something that we cannot do away with. So that is sort of the, so to speak, sort of the eyesore in our eyes, right? It's like, okay, you can scale storage, you know, and I didn't talk about this, but we have another piece on data warehousing where we offload database processing into the storage. So we minimize the amount of data that we put on the interconnect. So with all of that, with OLTP, the sort of eyesore we've had is that we need the network to scale our storage, right? To use a shared cache model. But at the same time, we pay this hefty cost of, you know, 100 microseconds on that. And when, you know, you compare and contrast to it like a persistent memory, it's just, you know, this is too much. We really want to optimize that. So that's why we pivot towards RDMA. And we really think that, as I mentioned, our caching is fluid. You know, whatever is hot of the moment gets promoted into the cache. So we really don't see a huge need in terms of, you know, oh, throw away all your disk and then just put, you know, this crappy, cheap flash and somehow, you know, build a solution for that, because we don't see any really performance advantages from that solution. And we definitely see a capacity sort of drop if you switch to that configuration. So that's why I kind of stick with, you know, when we have the high capacity storage servers with, you know, the tiered PMEM, flash, and hard disk is so far like the most popular choice that our customers have chosen. Sorry, I didn't quite catch that one.
So we have time for maybe one last quick question. So Jan, you asked about the, I'll just read it. So, which is, what is the drawback of the IO directory cache setting?
Oh, maybe Andy is
like
better. First, I'll tell you what Intel taught us. So the IO directory cache is actually the reason, okay, one thing I didn't get to mention that is you'll be like, Jia, you do all those RDMAs, right? RDMA to PMEM writes. How come you didn't detect this performance drop back then? And then when you only see it is through the CPU core. So what happens is that it turns out this IO directory cache was actually enabled for all IIO transactions. So if you do IO through PCIe, you automatically, regardless whether you go a remote core or local core, especially in the case of remote core, the IO directory cache is already enabled. So that's why we didn't hit any performance problems. But when we do the IOs through the CPU, stores through the CPU cores, that's when we get hurt. And then, you know, my understanding of that problem is that when you go and then do a write to the PMEM cache line, you have to, especially through a remote core access, you have to update the directory cache state. And to update that, the directory cache is co-located. The directory cache state is co-located with the PMEM data itself. So basically, you end up doing a read of that cache line, update the directory cache state, and write it back before you can issue the actual write to the PMEM DIM, because that's just the Intel update protocol. So with IO DC enabled, what ends up happening is that those cache lines, if you're always writing, let's say, similar cache lines, they may actually be residing in your cache, and in which case, and then even if it's not, it'll just read it from PMEM, which is no big deal because reads are pretty fast. It's the writes which are slow. I'll wrap up. I know Steve popped up, but and then what happens is that the directory update is then cached. It's not pushed back into PMEM. So instead of doing two writes, that directory cache state update is piggybacked with the write itself. So you only reduce it to one write. So essentially you reduce 50% of your write volume to PMEM, and that's tremendously helpful in the case when the PMEM write isn't, you know, as fast, shall we say, as the PMEM read. So that's the trick of IODC.
Awesome, thank you.
Thank you, Bill.